Welcome to our Gravitation podcast. Our first guest of the evening is Dr. Richard Feynman, American theoretical physicist who needs no introduction. Welcome to our podcast, Dr. Feynman. Can you start us off with an introduction on the laws of gravitation?
Now, what is this law of gravitation that we're going to talk about? The law is that two bodies exert a force upon each other, which is inversely as the square of the distance between them, and varies directly as the product of their masses. And mathematically, we can write that great law down in formula, some kind of a constant times the product of the two masses divided by the square of the distance.
Could you tell us more about the history of this phenomena or how it came about?
The history of the thing briefly is this, that the ancients first observed the way the planets seemed to move about in the sky and concluded that they all went around, along with the Earth, went around the sun. This discovery was later made independently by Copernicus after they had forgotten, that people had forgotten that it had already been made. Now the next question that came up to study was exactly how do they go around the sun? That is, exactly what kind of motion? Do they go with the sun at the center of a circle, or do they go in some other kind of a curve? How fast do they move, and so on? And this discovery took longer to make. The times after Copernicus were times in which there were great debates about whether the planets in fact went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on.
How did they ultimately discover the truth of the matter?
When a man named Tycho Brahe got an idea of a way of answering the question, he thought that it might perhaps be a good idea to look very, very carefully and to record where the planets actually appear in the sky, and then the alternative theories might be distinguished from one another. So Tycho, who was a rich man and owned, I believe, an island near Copenhagen, outfitted his island with great brass circles and special observing positions, situating chairs that you could look through little holes, and recorded night after night the position of the planets. It's only through such hard work that we can find out anything. When all these data were collected, they came into the hands of Kepler, who then tried to analyze what kinds of motions the planets made around the sun. And he did this by a method of trial and error. At one stage he thought he had it.
How did Kepler come to figure out his three laws of gravitation?
So he figured out that they went around the sun in circles with the sun off center, and noticed that one planet, I think it was Mars, but I don't know, was 8 minutes of arc off, and he decided that this was too big for Tycho Brahe to have made an error, and that this was not the right answer. So because of the precision of experiments, he was able to proceed and find that, to go on to another trial, and found, in fact, ultimately this. Three things. First, that the planets went in ellipses around the sun with the sun of the focus. The next question is, and going around the ellipse, how does it go? Does it go faster when it's near the sun, slower when it's further from the sun, and so on? And Kepler found the answer to this too. He found this, that if you put the position of the planet down at two times separated by some definite time, let's say 3 weeks, and then at another place in the orbit, put the positions of the planets again separated by 3 weeks, then the area that's enclosed in the orbit of the planet and the two lines that are separated by the planet's position 3 weeks apart is the same no matter what part of the orbit the thing is on. So that it has to go faster when it's closer in order to get the same area as it goes slower when it's further away, and in this precise manner. Some several years later, he found the third rule, and that had not to do with the exact motion of a single planet around the sun, but related the various planets to each other. And it said that the times that took the planet to go all the way around was related to the size of the orbit, and that the times went as the square root of the cube of the size of the orbit.
Our second guest today will speak about the expansion of the universe and its connection with gravity. I will let him introduce himself, but I doubt the man needs an introduction.
My name is Neil deGrasse Tyson. I'm an astrophysicist with the American Museum of Natural History in New York City.
Welcome to our podcast, Mr. Tyson. Could you start us off with a brief description about the nature of our universe?
The universe right now is expanding, and it's been expanding its entire life. And it looks like it will continue to expand for the rest of its life. And en route, from the beginning until now, the universe made stars and galaxies and black holes and planets and comets and asteroids, and in there's dark matter.
How is dark matter related to gravity?
I don't know what that is, but it's responsible for most of the gravity of the universe. Shouldn't really call it dark matter. That implies we know that it's matter. What it literally is dark gravity.
How is the expansion of the universe contradictory to the principles of gravity?
There's a mysterious pressure in the vacuum of space that is forcing the expanding universe to accelerate. And this is an action opposite the trends of gravity. If you add up all the gravity of all the stars and all the galaxies, it should slow down the expansion. And possibly bring it back. It wouldn't have to, though. When we look out at the expansion, we find the expansion accelerating. And we give a name to this. We call it dark energy.
Next, we have a famous YouTuber, Joe Scott, who's here to share a few misconceptions about gravity.
One of Einstein's big breakthroughs was what he called the equivalence principle, which is the idea that if you were accelerating at the same rate as a gravitational constant, it would feel to you just like gravity. Now, this is one of the things that flat earthers claim explains gravity on a flat Earth, that the flat disk of Earth is actually accelerating upward through space at 9.8 meters per second squared. And that's why we feel this downward force. But if you started accelerating right now at 9.8 meters per second squared, you would reach the speed of light in 354 days. That's less than a year. And since nothing can travel faster than the speed of light, that theory's pretty much out the window. Now, a common misconception is that gravity doesn't work in outer space, because we always see astronauts floating around in zero gravity. And if you're anything like me, then you grew up thinking that the further away you were from the surface, the less gravity affected you, which is why astronauts got to float around all cool like that. But that's not how this works. That's not how any of this works. The reason these astronauts are floating is because they are in orbit around the Earth. And orbit is basically a state of always falling. The best description of orbit that kind of clarified everything for me was actually Sir Isaac Newton's first thought experiment that led him to come up with the idea of orbit. And he basically imagined that if you could fire a cannonball far enough, that it would eventually fall along the curvature of the Earth. If you fired it further and further and further, it would eventually go all the way around the Earth. And if you get that ball going fast enough, then the gravitational pull of the Earth would only cause that ball to follow around the curve of the Earth, meaning it would continue to go around and around in orbit. So being in the ISS is basically like being in an elevator that's constantly plummeting toward the ground. Fun!